So let's look at the following example that deals with the Atwood machine. So let's begin. Suppose the mass of a counterweight is 1050 kilograms and the mass of an empty elevator is 800 kilograms, while the elevator carrying passengers weighs 1300 kilograms. Now we want to find the acceleration of our elevator going downward as well as the tension in the rope. So let's look at the following illustration of our Atwood machine described above. So here we have a pulley and the rope sits on the pulley, and this is a massless rope, and that means the force on this rope goes undiminished through the rope. So one end of the rope is attached to our elevator and the other end of the rope is attached to a mass, the counterweight. The mass of this counterweight is m subscript c, which is 1050 kilograms, and the mass of this elevator carrying passengers is m subscript e for elevator, which has a mass of 1300 kilograms. Now our elevator is accelerating downward, so it's moving downward at some acceleration a. We want to find what this acceleration is, and we want to find what the tension in the rope is. So what this Atwood machine basically does is this weight helps balance this side and slows down our acceleration so that our elevator does not accelerate as quickly. So to find our acceleration, we basically have to look at all the forces that act on this object and on this object separately. So, but before that, let's define which direction is the positive and which direction is our negative direction. So, we're only looking at forces along the y-axis, so we don't really even need the x-axis. But let's say going upward is a positive direction, going downward is a negative direction. So, this elevator accelerates downward, and that means this is a negative direction. This counterweight accelerates upward, so that means this has a positive direction. Note that as this decelerates downward, this accelerates upward, but they're accelerating at the same magnitude, just they have different directions. So let's look at all the forces along the y-axis on this counterweight m subscript c. According to Newton's second law of motion, we know that the net, or the sum of all the forces along the y direction on our counterweight, net F subscript c, is equal to the mass, so m subscript c, multiplied by our acceleration, our counterweight going upward. And that's why this has a positive sign. And this equals to the sum of all the forces. So what forces are acting on our counterweight? Well, one force pulls it downward, that's the force of gravity, and the second force pulls it upward, that's the force in the rope. So we don't know what the tension in the rope is, so we leave that as our unknown. So this equals the force due to the tension in the rope, which is, by the way, going upward, and that means this guy's positive, because remember, we define upward to be positive and downward to be negative. So that means the gravitational pull on this mass is going downward, so that's why we put negative mc, m subscript c, times the gravitational constant g. So this is our equation for our counterweight. Now let's find all the net forces acting on our elevator. So once again, we use second law of motion, and we see that the net forces on the elevator equal negative mass of elevator times the same acceleration, just going downward, right? Because this elevator is traveling downward and this counterweight is traveling upward with the same magnitude, just different directions. So that's why we have the negative, and that's why our A's are the same. Equals the sum of the net forces. Once again, the force in the rope, the tension in the rope, is going upward. It's pulling our elevator upward. So that's why this is positive. Likewise, the gravitational pull of the Earth on this elevator, having a mass of 1300 kilograms, is going downward, and that's why we say minus m subscript e for the elevator multiplied by our gravitational constant g. Now, notice that we have two equations and two unknowns. We don't know what our acceleration is, and we don't know what our force in the rope is, what the tension in the rope is. So, how can we solve for one of these using both of these equations? Well, what I basically want to do is I want to take this second equation and subtract it from the first equation. And that will allow me to cancel out my tension in the rope, my force subscript T. If I cancel these guys out, I'm left with one equation and one unknown. And then I can solve for my unknown, my acceleration. So let's do exactly that. Let's take this guy and subtract it from this guy. So m subscript C times A minus m subscript E times A gives us the minus is becoming positive, and we get m subscript C times A plus m subscript E times A equals. Now let's subtract these guys. So this guy we're taking away from this guy. So Ft minus mc times G minus this whole guy. So these cancel out. So we get, so this guy disappears, and now we get minus mcg plus, because this minus becomes a plus me times g. And now notice that on this, on the left side, there is a common term in both terms. So let's take the a out, and on this side, let's take the two g's out, and let's take the g out. We get a times mc plus me equals g times me minus mc. So we want to find what the a is. We know what these guys are, and we know what these guys are. So let's bring this over here, and we are left with our acceleration is equal to this whole formula. Gravitational constant g times our me minus mc divided by mc plus me. So we're taking the masses away, and then we're adding the masses and multiplying our result by g. So let's plug stuff in. 9.81 meters per second multiplied by 1300 kilograms minus 1050 kilograms divided by 1300 kilograms plus 1050 kilograms gives us 1.044 meters per second. So our elevator is accelerating downward, so our direction is negative at a magnitude of 1.044 meters per second. And our second part of the equation is to basically, or our second part of our problem is to find the tension in my rope. So notice that now I know what my A is, so I can use either of my initial equations, plug that value, this value into the A value, into the A variable, and solve for my force tension. So let's choose our first equation to solve for our F, or tension in the rope, F subscript T. So let's take this 1.044, plug it into this A, bring this guy to this side, add this to this, and we will get our force, our tension in the rope. And that is approximately 11,400 newtons. So my acceleration of the elevator going downward is 1.044, and this is accelerating upward at the same rate with the same magnitude. Now the force on either side of the rope is 11,400 newtons.